Okay, are you recovered from the previous 90 minutes? Then we have another 90 minutes ahead of us, and this time it's about statistical methods in high energy physics. So what's that about? So I divide this into two parts. The first part, we look into probability, the definition of probability, the different definitions of probability actually, and look at the properties of some data samples, and then from probability we go to probability density functions. And I show you a few that are used in high energy physics. And there's actually a very important theorem called the central limit theorem. Actually, I would like to, what is your background in mathematics? Have you had probability theory or some beginning of, in school or in the university already?
No, only in quantum mechanics.
Pardon?
Only from the quantum mechanics,
Okay. And have you dealt with probability density functions that describe, that integrate the one? Okay. Then it's not so complicated. And then I have a short come back to data simulation, but we look at it from a different point than actually yesterday. We just look at it from the point how we get from probability density to actual data. And we look into random numbers. So this is basically, this covers the part nature has basically the underlying nature is a probability density. When you simulate data, you do the same. You start with a probability density, and you go from there to a data sample. The data sample is then what we measure with our detectors. So the second part then of this lecture is how you get from the data samples back to the parameters of the original distribution. That's what's called statistical analysis. So this consists of two parts. First is event classification. That means you have a data sample, but you want to purify it. You want to throw out the background and keep the signal. So you want to classify the signal from the background. How to do this best? We look at statistical tests and look at the Neyman-Pearson lemma. And then we look into multiple methods like neural networks, boosted decision trees, and multi-dimensional likelihood functions. And this helps us to classify our event sample, purify our event sample, and the last part, the last 3-4 slides are then about the estimators. How do we get from the data distribution to the underlying parameters of the generating PDFs? And this comes back to the fitting what we had in the morning. How do you fit a model to the data? So in high energy physics, well, what we do observe is events, and then we measure the characteristics of events. We measure particle momentum, number of muons, energy of jets. In addition, we have theories, for instance, standard model, well measured, that predict the distribution of these variables. And the theory has also three parameters: the K constant, the Fermi constant, the Z mass, the strong coupling constant, the Higgs mass. And some of the tasks you do in the analysis is just to measure these parameters, to estimate them. Actually, you don't measure them. You estimate them from the data. You want to quantify also how big is the error on your estimation, because when you give a result in some paper, you give a mean number, and you give an error. And then also you want to, well, what you also want to do, but we don't look at this, is you want to actually find how your theory is in agreement with the data that you measure. So let's start. What is the probability? And we start with some very basic axioms that were set forth first by Komorov. And basically he said well, let's say we have a sample S of possible events of an experiment. So, for instance, you throw a dice. One possible event is throw a 1. Another possible event is throw a 2. Another possible event is throw an odd number. Or another possible event is throw a number larger than 3. We define mutual exclusiveness if events cannot occur at the same time. For instance, E1 and E2 are mutually exclusive because you cannot throw a 1 and a 2 at the same time. E3 and E4, on the other hand, are not mutually exclusive. If you throw a 5, you will throw an odd number that is larger than 3. So that defines mutual exclusiveness. So and then Kolmogorov went ahead and said, I define mathematical probability as a function for an event E, which has these 3 properties. The probability is larger than 0, larger or equal 0. If I have 2 events, the probability that one or the other happens is the probability of one plus the probability of the other if the 2 are mutually exclusive. And the probability that of all events is 1 if you sum over mutually exclusive events. So this is straightforward. And first, before we go into any interpretation what this actually means for physics, let's look at some rules that you can derive. One of the rules is you can define the opposite event, so the probability of not event A is 1 minus probability of A. You can, the sum of the 2 is then logically is 1, so that either something happens or the opposite happens, one of the 2 is always true, so the probability is 1. Probability of the null event is 0, and there are a few other rules about the inclusion and about the combination. There's also something called conditional probability. How likely is something if something else has already happened? So you can, and this is defined like the probability that both have happened divided by the probability that only one has happened. So if you look at this, let's say this is probability space, these are all little events, and I define one event B, and I want to find out how likely is it that this event A happens if B has already happened. So then I know this is basically the fraction B and A, which is this one, divided by the whole thing. So if B happened, the likelihood that it is this part is basically the fraction of this to the whole thing. So this is called a conditional probability. If you want to think about this in a different way, if you are supposed to guess, your friend asks you, guess which day I'm born, you guess Sunday, you have a chance of 1/7 that you guess correctly, right? So, but after he tells you, oh, it was I was born on a weekday, well, then if you guess Tuesday, then the chance that you're right is 1/5, because he then, under the condition that he was born on a weekday, Tuesday is 1/5. And if you apply this formula, see Tuesday and weekday is 1/7, and probability of weekday is 57, and you get to this number. Independent events, these events that don't overlap, follow this formula for the conditional probability. No, not that they don't. The conditional probability that something happens under the assumption that something else has already happened is equal to B from A if they are completely independent. So for instance, if the hint of your friend is, I was born on a rainy day, the weather is completely independent from his birthday, then your guess is still one, so this is basically no information, so you guess Tuesday under condition it was a rainy day, probability is still 1/7. So this and this is the same because they are independent. So now we have these 3 axioms. We already derived some of the laws, but you can go much further. And as the whole probability theory is based on 3 axioms, and then we went from there on. But we don't want to go there. What we want to do is we actually want to find some interpretation of the word probability for high-energy physics. And there are three definitions how you could define probability, and two of them are in high-energy physics. One is more of theoretical nature, but I show you also of them. The first one is the probability as a frequency limit. So you perform a repeatable experiment n times. The outcome is n outcomes you test, the ensemble, and you count the number of times that a certain event x occurs. And it occurs nx times. So then this fraction nx over n, so how often my event happens out of all events, tends toward a limit, toward a fixed number. And that is defined as the probability of the outcome x in the frequency, approximately, in the frequency limit. So you say, so I throw a dice 100,000 times, I measure 33,000 times, it's a 6. Therefore, I can then define my probability at 6 as 1 over 6 because it goes to the limit. So is this useful in daily life? No, the answer is no. And the reason is because the outcome of the experiment depends very much on the ensemble. So for instance, well, this is an example that Richard von Mises, he invented this whole theory in the beginning. He made an example about clients of a German insurance company, and they found that 1.1 of their male clients died between the age of 40 and 41. But then that does not allow you to tell anything about Mr. Schmidt, who has a policy with his company, of his chances to survive to die at this age. Because what happens, for instance, if Mr. Schmidt is not only part of this insurance company, but also is a smoking hang glider pilot, then his chance to die is much higher because it's drawn from a different sample. So you have to be very sure that when you make any assumptions about the treatment, when you measure this, that the underlying ensemble is actually representative. And this is, nowadays people make a lot of money with doing demographic studies and shopping behavior, advertisement, and then to get representative samples. Another problem is with this is the experiment must be repeatable. There's no use in looking at the limit if I cannot repeat the experiment. And these are what makes this definition in daily life not very useful. However, for high-energy physics, it's very useful, and we use this a lot because laws are universal and unchanging. So the ensemble that we draw from, no matter if you do an experiment at Fermilab or at SLAC or at CERN, the underlying ensemble is always defined by the physics that creates our events, and that's the same everywhere. It's the same cross sections. Anything. The only thing that's different is the energy you run at, but this is basically under good control. And of course, it's repeatable because the experiments, events are all the same. The conditions are always the same. So in high-energy physics, this is basically what we use most of the time when we do analyze our data. The second definition of probability is called propensity. And this, you can, if I tell you what is probability of a die showing a 6, when you roll it, you immediately say 1/6, right? It's sort of an intrinsic property of the dice. Or if you have a sack full of red and green pearls, and you draw one out, you can immediately calculate the probability because it's sort of intrinsic to the experiment. Or if you play roulette, 1 over 33, 1 over 37, that you get a 0. So this you can see immediately without having to collect any data. It's basically a single case probability, and they call it propensity. However, how do you measure this? You know it because it makes sense, but you cannot measure it because as soon as you measure it, you basically take an experiment and you move back to the frequencies approach. So hence propensity is always there, but it's more of a theoretical way of looking at probability, and you shouldn't worry about it. The third definition of probability, before going there, I want to tell you about Bayes' theorem. So we had looked at conditional probability. The probability something happens under the assumption that something else has already happened was the product, the probability of both happening divided by probability only one happening. So if you write this the other way around, you can also write it this way. It's completely symmetric. And then you divide, and then you get this. So this is comes directly from the Kolmogorov axioms, and it's independent of which theory you like, frequentist or Bayesian approach. This is uncontroversial. I'll tell you in a second how you actually think about this Bayes theory, and I'll give you an example. But first, let me tell you about the third kind of probability, which is called the subjective probability. So if you have hypotheses, the probability of a hypothesis A is it's a vague thing. It's the degree of belief that A is true. So the frequentists and a lot of financial physicists are frequentists. They say this is really unscientific. But if you apply this degree of belief method to Bayes, so you look at this formula. So on this formula we have this 4 terms from the Bayes theorem. This is the underlying probability that some hypothesis is true, and we assume this without knowing anything. We have not looked at any data yet, but we also have made predictions that if this is true, then we should be able, for instance, to observe a certain result. Bayes' theorem now tells you, if we observe a certain result, how likely is it that this underlying assumption is true? So this is called the prior probability. So this is the belief, the degree of belief that this is true. And this is after the measurement, basically the degree of belief that this is still true. So this approach, while it's not used when you analyze a lot of data, in the end, this is actually very useful to make a final statement about the probability that the result you found is consistent with the theory you were investigating. This last sentence, and it's the same to you on the next slide. So how do you interpret Bayes' theorem? Maybe this helps you a little bit to understand. For me, I always just struggle. So the underlying theory, this is the assumption theory might be true. And then this is if the theory is true, how likely do you see a result? And this tells you, if you see a result, after you see a result, how likely is it then that the theory is true? So for instance, consider a theory that forbids a certain result. So under this theory, I can never observe result R. This is what this says. Then the probability that this theory is correct if you do observe the result is 0. Because if the theory tells you it cannot happen, but it happens, then the theory must be wrong. So an observation of R will disprove the result, the theory. So this is how the Bayes theorem turns the whole thing basically around. Maybe that's too strong a statement. If a result is unlikely, then the theory is unlikely under observation of R. So if the result is unlikely, but suddenly you observe the result, then the theory becomes unlikely, right? And the other way you can also turn this around. However, there's one problem with this denominator. So this denominator, if it becomes large, basically that means the probability of the result is large. That means not only my theory can create this result, but a lot of other theories can also contribute to this result. Then I cannot really make a strong statement about the a posteriori theory. So you always hear about Bayesian approach, Bayes theory. So this is what that is driving that. So now let's look at the law of total probability. That's a very, very simple to understand law. So here's the law of total probability. Probability of B, which is this red area, is the sum of all probabilities of B and AI. So the AI are the little blue region probabilities, events with their probabilities. If you take the intersection, it's always these. Well, so these are the intersections, and if you sum them all up, you get the total probability of B. So this is the law of total probability. You can then use this. Remember, this P from B was the denominator of the base law, and you take this and put it here, and then the space theorem written in as with the denominator of the sum of all these single events. So now let me give you an example from, let's say you have a meson beam which consists of 90% of pions and 10% of kaons. So we have A1 hypothesis that that's a pion, A2 is that it's a kaon, and the Cherenkov, when you have a Cherenkov counter that's sitting in a beam, the beam goes through, and it gives you a signal on pions. It's designed to give you a signal on pions. So it's 90 for pions, but you have a fade rate of 6%. It means for 6% of the kaons, it gives you an accidental signal.
Can you explain what comes from accidental signal? I can't understand.
Accidental signal. So this Cherenkov counter is a device that measures the particles, and it's supposed to beep if there's a pion coming through, and it's supposed to not beep when there's a kaon coming through. Because it's designed that way to give a signal on pions, but not on kaons. But sometimes a kaon actually makes a signal, but this is not wanted, so I call this an accidental signal of the Cherenkov counter. So the question then is, if we see a signal in the counter, how likely did it come from a pion? So from these numbers, we can actually use then the Bayesian law to find out that if we see a pion, it's 99.3% that it actually came. If we see a signal, then that it is a pion is 99.3%. This is what Bayes' law gives you. And it basically takes into account that you have much more pions than kaons, and it takes into account that you have a certain efficiency and fade rate. And you put this in. So the 95% is, if it's a pion, then we see a signal is 95%. Same here, the same number. Then we have to weight this by the 90% of pions, and we add the 6% fade rate of the 10% kaons. And we have to give the a priori probability of 90% of pions.
So these numbers are something that are constant, or it's changeable?
No, they are constant for this experiment. So this is how the Bayes, we can look at Bayes' law. So now in high energy physics, which of the frequencies we have probabilities we use? I already told you the frequency. Well, each has a strong point and the shortcomings. All are consistent with the 3 Kolmogorov axioms we had in the beginning. In particle physics, the frequency approach is most often useful because we deal with large data, we define the probability of something we measure over a long time. The subjective probability can provide you with a more natural way of thinking about and treating non-repeatable phenomena. So systematic uncertainties, probability that you, for instance, discovered SUSY, or the Higgs in your analysis, you can treat with the Bayesian approach by turning around the statement of theory and result. Yeah, if you read the literature, the names are often confusing. The Bayesian score of best is to use frequentist and Bayesian names as the names for these two theories, and then the others. So now let's come to the data. Here you see an image of the flags in the bubble chamber from CERN, which are hit by a pion beam. Here you see an image of a Higgs event in a proton-proton collision at the LHC. So an high-energy physics event is basically particle interactions which are measured by our detectors. And what we measure is then random variables of these events. And named distributions which come from the underlying physics processes, of course, and which is what we want to find out. And here's an example about the things that you can measure. You can energy, momentum of the particles, the angle, number of hits in a certain detector, the charge, the delta of the time. So let's look, if we have a data sample, there are various properties that you can find immediately. You have a data sample, which is let's say, n data points. You can present them either unbinned, as the list of numbers, or you can put them in this histogram and present them unbinned. You can calculate the arithmetic mean of, by summing over all of them and dividing by n. Or when you have only binned information, you can provide an arithmetic mean by summing over the histogram and dividing by n, but then you have to build a sum like this. The arithmetic mean of a distribution doesn't tell you everything, because if you look at the German town of Kleinmaischeid, the arithmetic mean of the town is somewhere in the center. But if you look at Europe, the arithmetic mean of the center of the European Union in 2005 is the same point. But the European Union is much bigger than Kleinmaischeid. So what's actually important is also to look at the variance, which is when you sum over all of the data points in your data set and you build the quadratic deviation and divide by n. So this is the variance and arithmetic mean. Standard deviation is the square root of the variance. The same is not only true for one dimension, but also for 2 dimensions. There you have tuples of, so you also have n data points, but each data point is 2 numbers. You can, again, unbind. You can also bin it. But when you have 2 variables, there's actually additional data sample, and this is the covariance. And that tells you, it tells you how the points are related, the 2 variables are related to each other. If they're completely independent, so for instance, you have, you have 2 independent variables, then they are distributed like this, and you have no covariance between them. If they are very correlated, for instance, momentum and energy of a particle are very correlated, of course, then you have, they look like this. And the way you determine this, you can calculate the covariance, which is always the product between one variable, deviation from the mean, and the other variable's deviation from the mean. If they both always deviate in the same direction, then you have a high covariance. If the deviation is random, so this goes down, this goes up, or vice versa, then you have a low covariance. If you normalize this with the standard deviation, then you get a correlation. Here are some examples about where you find correlations and where you find uncorrelated measurements drawn from a sample of the dials. So now let me come to a probability density function. So let's say you have a variable x with an outcome of the experiment. The variable x can take a value, dx. Probability that value dx is found in an interval x and x plus dx is given by this function times dx. So this defines the probability density function. So in some areas where you find a lot of your events, then the probability density is high. If you find in areas where you find only few events, probability density is lower. Since the event must be somewhere, the integrated integration over f on x must be 0. It must be 1. Probability has no dimensions. F of x, the probability density must have a dimension because it's a density. You see here, if you multiply it by the x, you get a dimensionless number, so the dimension of that one is 1 over the dimension of x. That's important to know and also helps you in cases to understand what's going on. So the same way that we have defined for data sets, you have to find the mean and we have to find the standard deviation. The same way you can do that for probability density functions. For probability density functions, the mean, what we have the mean in the data sample is something, it's called the expectation value, which is the average x. And you get this by integrating over the function multiplied by x. So this is then the expected value. The variance is defined also very similar to the variance of the data set. It's defined that way. And it's also the integration over the average squared deviation. You can also define an expectation value for not just for the variable x itself, but if you build a function of which is a function of x, h1 x, then that function also has an expectation value. So I already said these, and these are averages for the PDF. With the dash on top, we denote the average over a real data sample. And there's a law which is called the law of large numbers. So if you have a very large data sample, then the mean of the data sample approaches the mean, the expectation value of the PDF. So I told you the PDF is a density. Here values are more likely, here are less likely. If you integrate from here to here, you get basically a number that for the likelihood for events to be in this range. And if you integrate up to here, you get a likelihood that they are in this range. And if you integrate all the way to the end, you get to 1. And this is basically called the cumulative distribution function. So it's defined by the integral from -infinity to a certain point. It's called the cumulative function at that point. So it's always, so this value here, 0.5, is basically the integral from here to here. Okay. Are you with me so far? So how are this related? So PDF uses its probability density function. So if you have a histogram, you fill it with the outcome of the experiment and bins. You will see here a histogram. Here you fill more bins, you fill more bins, and you fill more bins. At the same time, to make the bin width smaller and smaller. So in the end, you have Ni is basically the fraction of events found in a region, as we have defined before, and you make this delta x goes to 0, while the number of events that you put in goes to infinity. In the frequentist approach, that basically defines your PDF of the underlying process. But since we don't have infinite data, we have to use approximations. Now, what we have looked at in one dimension, we can also look at in many dimensions. So let's look at here in n dimensions, but in the drawing only in 2 dimensions. The probability of a certain event lying at x plus dx in the first variable, and at x2 plus dx2 in the second variable. So, which is basically this probability here, is basically called the joint PDF, the multidimensional probability function. So you can maybe imagine it's like for each point square here in this 2-dimensional plot, the probability density you can imagine as the 3rd dimension, and so it's a function of all the variables in the input parameter space. Is that sort of so it's basically a function from from n dimensions into 1 dimension. And again, it must fulfill the normalization criteria. If you integrate over the entire space, then the integration must be 1. because your event must lie somewhere in the event that happens has to be somewhere in the parameter space. Okay, so marginal PDFs and independent DESY. The marginal PDF, let's say we have an example here in 2 dimensions. In this dimension is a Gaussian distribution with a mean that goes to higher values, and in this dimension it is an exponential like this. So the marginal PDF is basically a projection of the parameter space onto one axis. So this is the formula. You have your joint PDF, which is in n dimensions, but you integrate it out over all dimensions except the dimension chain. And that gives you your projection in the dimension chain. So basically, yeah. So these marginal PDFs are projections of the joint PDFs onto the individual axis. So basically, if you look at this mountain here from this side, you would see the Gaussian. If you would look from this side, you would see an exponential decay. If you have any questions about these PDFs, please shout. So basically, what they are is in your input parameter space, at a certain point in the space, they tell you how likely it is that that your event would end up there.
I have a question. So when you marginalize over a variable, it means you are not using any information from that variable?
No, I think you use only that variable, and you neglect all the other information because you integrate everything else. You integrate out.
Okay. So marginalizing over a variable means you are integrating over the other variable.
That's right. Yes. So I marginalize the variable chain by integrating everything except chain. So this is a bit difficult to understand when you look at the formula. It's called the conditional PDF. Again, we have our 2-dimensional parameter space. A conditional PDF means that we want to consider, let's say, one of the variables, x in this case, as constant, and want to see how the PDF of y looks at this point. So basically, we said we have what this turns into mathematically is a conditional PDF. Here you have the choice PDF. You divide by the marginal PDF, and what you get is a conditional PDF. So this is basically a theorem applied to PDFs. And then when you have this conditional PDF, you evaluate it at a certain point x1. Sorry if you cannot see it. And you evaluate it at point x1. So basically you take out this slice out of the space, and then basically have the joint PDF evaluated for x equals x1, and you have to basically the division by the marginal PDF here is just to normalize everything. So if you look at for x equals x1, you might get this distribution. If you look at for x equals x2, you might get this distribution for y. So this is called the conditional PDF. You set a condition on one, and you look at the other. Okay, let's look at this bit less theoretical, but we look at some examples. So these are distributions that are common in high energy physics. Most of all is the Poisson, the Gaussian, and the binomial are very important. The other ones are also important, but maybe less. So here I list where you use them in high energy physics. Uniform, for instance, for Monte Carlo. This actually shows you often have to throw uniform numbers and then turn them for the Monte Carlo generation. Exponential decay time of particles is exponential. Gaussian is very important because of the limit, this central limit theorem. when you have a large number of measurements, the errors become all Gaussian. Landau and Cauchy are mass of particle resonances, ionization, energy loss, chi-square distribution. You have a little bit in the morning. It tells you about the goodness of a fit. The chi-square tells you about the goodness of a fit, and if you do that many times in a toy monocle, for instance, this chi-square behaves like this distribution. So the binomial distribution looks like this. So when is it used, for instance, if you have a fixed number of trials, let's say n trials, and the outcome is a binary outcome. It can either this can happen or this can happen, but with a probability of p. Let's say you have a fake coin. 40% of the time it can end up fall down head up, and the other 60% it tails up. So then you could calculate, if I do this, let's say 100 times, the probability is 40% for heads up. What is the distribution that I get? What's the likelihood that I get, for instance, 10 or 20 times heads up? So then you look at this, you calculate the probability according to this. The mean value is just the number of trials times the probability. So if the probability is 40%, you do this 100 times, the mean expectation is that 40 times it ends up on the head. So that is a very trivial distribution that one can easily visualize. For a song distribution, it's something that is a bit more difficult to understand. If you have a discrete distribution for fixed numbers, for integer numbers, but there's no notion of trials. You don't have n trials. Rather, what you have is that in a certain amount of time, it could happen lambda times that some event occurs. For instance, you wait like a day, a thunderstorm, you count the number of lightning flashes. This is a rare event, and it follows the Poisson distribution.
So lambda is real number and R is an integer, right?
Lambda is an integer.
No, R is an integer.
Oh, R is an integer, yes. Lambda is the fraction of in a certain time, an average that happens lambda times. So in that sense, the binomial distribution turns into a Poisson distribution if you go to small probabilities and large number of such that the number of trials times the probability is a constant. And so maybe you can see this here. You're basically then it's difficult to see. So how should I? Well, the reason why this distribution is important in high energy physics is, as it says, the law of small numbers. If you do, for instance, a fit to a histogram, and the number of entries in a bin is small, then the error in that bin doesn't follow Gaussian anymore, but it follows the Poisson distribution. So in the end, when we, for instance, look at the maximum likelihood fits, where you have to assume the distribution that you have to use for your fit, you have to assume the Poisson distribution. And for that, it's important to know that the mean of the distribution is the lambda, and also the variance of the distribution is this lambda. So, and I said lambda is basically the number of events in a certain fixed amount of time. The average number of events in a certain fixed amount of time. Well, I think I'm running out. Otherwise, it's a very interesting example. This was this Polish guy Ladislaus Bortkus. He came up with this distribution, and he studied it in the number of fatal horse kicks in the German military in 1800 something. And he found it's a very rare event that you killed by a horse if you're a soldier, but it happens. And he found that the distributions that this happens follows exactly this Poisson distribution. So the Gaussian distribution, you already know, it's a distribution that has, or looks like this. It has a mean that is also the same as the parameter mu in the formula, and has a variance that is the same as the parameter sigma squared in the formula. What might be a bit confusing is that mu and sigma also denote mean and standard. So they denote, these are the symbols for mean and standard deviation for any distribution. But there are also these names here and here. However, since they turn out to be exactly the same, it makes sense to use sigma here and mu here. But I want you to be aware that this is not necessarily has to be that this naming is chosen because of these properties. If you take this formula and you shift your x by mu and you divide it by sigma, then you get a formula like this, which is then called the normalized Gaussian or the standard Gaussian. One thing that I told you before about the cumulative distribution of a PDF, where you integrate from minus infinity to x. For a Gaussian, this is cannot be done analytically, but you have to do that numerically. It's called the error function. But however, since this is a very important property, because, well, I told you before, Gaussian distribution describes errors. So if you want to quote 1 standard deviation, 2 standard deviation, 3 standard deviation errors, you need to integrate to certain values here. So therefore, these function called upper phi, which is the cumulative distribution of the standard Gaussian, is very well tabulated. So for all x, you can read these numbers from tables. And here I have given you the numbers for 1 sigma, 2 sigma, and 3 sigma. Are there any questions about this so far? Yes, yeah, that is important. As I said, the central role in the treatment of errors, and to come back in the central limit theorem, which I think comes soon. Other distributions, the exponential, I've shown you already, the exponential decay of particles. With a lifetime of c, they follow this behavior. You can see here, it's just an exponential decay. The uniform distribution is between alpha and beta, the two parameters, is the size is beta minus alpha and it's 0 outside. So you see that's the distribution, and if you integrate, of course, it indicates to 1 because of this. And it has a mean and a sigma like this. So sigma is beta minus alpha squared divided by 12. The bright Wigner is a very interesting, if you do search for particles, then it basically gives you the shape of a resonance. And here in the description you see the gamma, which is the decay rate or the inverse of the lifetime. Particle with a long lifetime has a small decay rate and has basically a very small width. Particle with a very short lifetime, as so-called resonance, has a very wide width. And the shorter the width, the wider the resonance is. Chi-square distribution looks like this. Encountered this in the morning, and it describes the distribution of the goodness of fit result upon repetition of the experiment. So these are the common distributions that are used in high energy physics. Let me now come to a very important theorem, and that might not seem to be important on first sight, but if that wasn't there, if that wasn't true, a lot of the methods that we use would not be applicable. And maybe you can only see this after a while working with these things. So if you have a variable y that is produced as the cumulative effect of a many other independent variables. Let's say you have variables x, y, and which are independent, and you sum them up. Then the sum follows a Gaussian distribution. Then n goes to infinity. So I'll give you an example in a second. And the mean of the sum distribution is the expectation value is the sum of the expectation values of the single distributions. And the variance, the same, also adds up in the limit when n goes to infinity. So what could be a good example? Let's say you have one dice and you throw numbers, all 6 numbers are equally likely. So it's a uniform distribution between 1 and 6. If you have 2 dice and you throw them together and you sum up the 2 numbers, then you have a distribution, well, 2, at 2 you have 1, at 3 you have 2, at 4 you have 3, and it goes up. The 7 is comes the most often, because it can be either 1 and 6, or 2 and 5, and so on. And then it goes down again. 12 is as likely as a 2, or no, it's just 1 out of 36. So it already has a P shape. If you then take three dice, it becomes already more like a Gaussian. To throw a 3, you have only 1 choice. To throw a 4, you have 3 choices. So it's a difference of 2. But to throw a 5, you have already 6 choices. So it goes a bit up again already. So it more and more becomes like a Gaussian. So this is what the central limit is about. The sum of independent variables.
Sorry, I have a question about previous slide.
About the central limit theorem?
Yes. No, one thing.
Okay.
Sorry.
This one.
Yes. Last lecture we said that chi-square is the difference between histogram and the fit function. Yes. But I can't make the bridge between this
and
function
this
and...
Yeah. Mm-hmm. So, remember also in the last lecture we had this point Monte Carlo, where we had, so you do a fit, and of a histogram with n degrees of freedom, let's say, and you repeat this fit 2,000 times. So the chi-square you get every time is a little bit different.
Yes,
right? Sometimes
converts to 1. It converts to 1.
No. The chi-square of each single, sometimes you have a bad fit, sometimes you have a good fit, sometimes you have an intermediate fit. If you then put all these chi-square into a histogram, that is in another lecture, it becomes a shape that looks like this one here. And you have different shapes here, and the differences are the number of degrees of freedom. I think this one is for 10 degrees of freedom. It looks like this. In the morning we had an example with 40 bins histogram. A few empty ones we had about 35 degrees of freedom, so the chi-square distribution looked like this. So it's the repetition of the experiment which draws the distribution. Not a single experiment is one chi-square, but if you do this many times, so for instance today you get 1,000 events when you experiment, tomorrow you get another 1,000, and tomorrow the day after you get another 1,000. After 2 months you have 60 numbers, and you put them into a histogram, and they will look like this chi-square distribution. So it's So in this first part I introduced you to the two main probability approaches, and showed you properties of data samples and also PDFs. And well, I hope it became clear that the PDFs are the underlying distributions from which the data samples are drawn. And we have looked at properties of PDFs and some examples. Now in the second part, what I would like to do is go from the data set back to how we get the parameters out of the data set. And well, it goes three parts. First, the purification of the data sample, then the estimation of the parameters, and well, error propagation. I think I'll skip. Just. But before we go there, I thought it might be interesting to have a little intermezzo about Monte Carlo simulation. So when we look at data and we want to infer something about a probabilistic process that produced that data. In order to do that correctly, we have to do some preparation. We cannot just today look at the data and tomorrow get a result out. And so the preparation we have to do, we have to tune the signal and background separation to achieve the most significant signal. We have to check the quality of the estimators, and I'll show you later. And we have to find statistical methods. Yes, and we have to, basically what we have to do, we have to check our analysis before we do data, we have to check it on Monte Carlo. And for this we have to simulate our data distributions. We have to simulate our data based on the distributions of known parameters. So how do we do that? First we have a random number, sequence of random numbers. To simulate the particle collisions, you simulate decay, we simulate the detector response, and then Joerg showed you all about this, the generators, and then the hadronization, and then the detector response simulation. Everywhere we need to generate random numbers, first uniformly, and then we have to transform it according to some rule into a desired PDF. And so first, maybe I want to pick, because that was of interest yesterday, random numbers. So it's not so easy to generate random numbers uniformly between 0 and 1. In a computer, you can have true random numbers in computers if you have some special hardware. This hardware, what they do, they use different sources of entropy that also are on your computer. Your computer is not always deterministic. For instance, there's thermal noise in your computer. There's noise on your sound card that you can use. There's the I/O time it takes to write data to your hard drive. It's actually a random process, purely random. And there are other types that you have to plug into your computer that also uses thermal noise from external sources. But these are really expensive, and you cannot really write software that relies on that, because the computer where you send your jobs to might not have this hardware installed. So the most often in computers you use random numbers which are pseudo-random, which means algorithmically determined sequences. In root, there you have 4 different ones: t-random, 1, 2, 3, and 4. This is a very simple one based on the BSD rand function. Has only one internal state of 32-bit and a short period of 10 to the 9. Then you're back at the beginning. So this is not that useful, maybe for short tests. T-random 1 is based on the rand lux, has a lot of internal state, and therefore a very long period until you're back to where you started. It also has something which is called a luxury level. That means out of 4 random numbers, I throw 3 away. It's very slow, but it's the default in Atlas simulation because it's very good. At least I think it is.
I don't know.
Then there's another, there are 2 other ones. This one is actually the one that is based on the Sandwich, so that's the one that's default in root. If you use the G-random, it's using this one. And if you already discussed, if you use seed 0, it uses random seed. So now you have a uniform distribution, but what you really would like is something according to this distribution. The way you do that transformation from here to here, well, you have to make sure this area and this area is always the same. So like this, so this is what you require. If you write this as a formula, the integral here is just this r prime. If you integrate to here, this is r prime. If you integrate here from minus infinity to x from r prime, which is this point, the function, cumulative distribution. And if you then have these two parts and you solve for x of r, then you basically get a description how you turn your random number, uniform random number r, into a number x of r, which then follows this probability distribution. That is very neat. Here I give you an example for an exponential decay. And if you throw a random number, then you transform this number and put a histogram. You can do this as a homework if you like, then you get this nice decay. However, this is not always possible to learn this function. So what people do is they use an accept-reject method. If you want to have a PDF, if you want to have a data sample that follows this PDF, you throw random numbers. Well, for instance, imagine you draw, or maybe this PDF. You draw this PDF on a piece of paper, and you throw random numbers. Well, you drop the pencil on this piece of paper, and every time the pencil lands inside this area, you keep this event, and you put the x value into the histogram. If it lands outside, you don't keep it. So in formula, you throw x uniform, x min, x max, u uniform between 0 and f max, which is the maximum value, and then you keep it if the u is below the line. And then you get, actually, you can throw a nice PDF according to any distribution that you have. So Monte Carlo simulation in energy physics, I think I will not go into this because I told you everything about that. Event generation, detector response, data. So from the detector response you get simulated raw data, which you then put through your data reconstruction. That is the same then for Monte Carlo simulated data, and for the real data from the detector, you basically run both times the same algorithms. And then basically what you have is simulated data that would look like that went through the same treatment as the real data. And this simulated data you use to estimate the efficiencies of your methods. For instance, you count how many events that I put in, I actually have found. That way you know how efficient your methods, your data reconstruction, your detector, everything else is. And you can use this data to test your parameter estimation. So I think nature or theory using probability gives us data. Given these distributions, how will the data look like? Simulated data or real data? Doesn't matter. Now the question is the other way around. We have data, simulated or real, through statistical methods. Given these data, what can we say about the correctness of the parameters, the correctness of the theory, the parameters, or of the distribution functions? So what can we say about nature? So a typical Hep analysis might look like this. This is a plot shown very often. Down here you have the center of mass energy of the collider. Here you have the various physics processes, how their cross-sections, how likely are they occurring at this energy. And if you look, here this is the Higgs. It sits down here. LHC total cross-section is up here. You see it's 10 orders of magnitude. So finding this is be difficult. But it can be made a little bit easier by doing the following thing. So you measure your events, you measure momentum and distributions, you measure the number of tracks, whatnot. Everything you can imagine might be different for the signal you're interested in and for the background you're not interested in. Anything that might have a discrimination power between signal and background. And then you put this into, in this example, maybe a neural network, and you get the neural network takes the maximum of information out of all these and provides you basically one output with the signal on the left side and the background basically on the right side. And you can, if you say, I only keep events that are on this side, you already purify your signal quite a lot. And then you look at a variable that you have not considered yet, for instance, here in this example, Dietrich invariant mass. And before the cut of the neural network, it might look like this. After the cut of the neural network output, it might look like this, and you can see the peak clearly. So once you have done this purification process, you then, from signal Monte Carlo again, you have found my signal distribution for the Dietrich mass looks like this. My background distribution looks like this. And I take the sum of the two, and I fit the sum of the two to my signal, to my combined distribution that I find from data. And doing this basically gives me, if the fit works correctly and everything is done correctly, it gives me the fraction of this part and of this part by adapting by adapting the fitting function. And so this is how it would look like. First you purify your event sample, and then you fit for the signal fraction.
And a quick time in the meantime, we will do these things tomorrow.
So you better pay.
You should better pay attention.
Okay. So let's come first to a part that I like very much, because I'm working on this in my spare time. This is event classification. And the plots you see here are from a package called TMEA, which is also part of root. If you check, you'll find it in there. And well, the principle is the following. So we come back now to this neural network and how do we make our event sample. So let's say we have a blue signal region, a red background region. We consider only two variables, and we want to find how do I best get my signal out while throwing the background variable. I can put cuts, let's say smaller than this one here. I can maybe put one linear boundary, or maybe I can put a non-linear boundary between the background signal region, and then I keep only what's in my signal region. But how can we draw these boundaries in an optimal way? And this is where this multivariate event classification and the machine learning comes into play. So maybe in other words, you have n input variables that you found that they have some power to tell me it's a signal or background. And these n input variables have different, so I said they have some discriminating power, because for instance this variable looks like this for the background, but like this for the signal. So that would already be good if I keep everything like this and throw away these events. But we can do better, and for this we use these event classifiers. What they do, they take all the information out here in an optimal way, and they are a function basically from n-dimensional input space into the one-dimensional output space. And what you get here is then a PDF for the background. So for the background you get what the classifier tells you. You take the background event, put this through this function, and you get the output PDF for the background and for the signal. And then you can say, okay, everything that lies on the right side I accept as signal, everything on the left side I reject as background.
Red and blue histograms on the left-hand side, how are they normalized? Are they normalized?
Good question. They are not normalized. They don't have to be normalized. And actually, I'll come to this later. But this is an important point that to define a good qualifier, what you want to do is you want to keep the background efficiency keep low, this part low, and the signal efficiency this part high. But the normalization of the signal for the background, so of this to this, is not important because the background efficiency is this fraction compared to this fraction, and the signal efficiency is this fraction compared to the overall signal.
Sorry, I don't exactly understand how you separate blue and red histograms. So in your data you have only one histogram with everything?
Okay, yes, that's the important part which I should have mentioned in the beginning. So this is Monte Carlo, and in Monte Carlo you know if it's signal and background.
Yeah.
So that's why Monte Carlo is important, because Monte Carlo, for one thing, helps you to train your classifiers.
So how do you select the cut in the end? By which of
I'll come to this.
Okay,
So convention in literature, the background, I have it always in red, or call B, is the hypothesis H0. So if you, in the literature, they don't talk about signal background when they talk about this. But they talk in more general terms as the null hypothesis and the alternative hypothesis. The null hypothesis is not an observed signal, therefore background, and the alternative hypothesis H1 is the signal. That's just a clarification. So this is a lot. So what you do, I showed you already, you have a test of the background hypothesis. You specify, you create this test by specifying it's called critical region in the literature, but what I call it's the signal region. So, and what you want, you say an event is in the signal region under the background hypothesis. So I say, what is the likelihood that the background event I accept as signal? This is what this formula says. And you want to keep this small. So alpha should be small. Background events should not be exactly the signal. This alpha is also called a type 1 error. So type 1 error is those truly background but accepted as signal. And if you go back, it's basically it's truly background, so it's a red curve, but accepted as signal on the right side. So this part here is the type 1 error. Type 2 error, also called beta, you accept signal events, you reject signal events as background. So you accept the hypothesis it's a background, although it's a signal event. You can write it like this, and it's called a type 2 error. It's just the opposite, the other error you can make. Efficiency, signal efficiency, keeping is then defined as 1 minus beta. This is beta, the signal efficiency is going to be 1 minus beta. And the background efficiency, which you want to keep small, is basically this part is alpha. So there's one important theorem that you cannot, this tells you how good you can do. You cannot do better than, so what you want to do, you want to keep alpha and beta small. And to keep alpha small, which was basically the background in the signal region, right? So you want to keep that small, the background efficiency. And you also want to keep beta, which is 1 minus the signal efficiency. Signal efficiency you want to keep large. So beta, which is 1 minus the signal efficiency, should become small. So alpha and beta should become small. If you look at these formulas, that means this should be small, and this one should be large. So you want, and the likelihood ratio test tells you there's the ratio of the two, and says this should be large. You only want to define a signal region such that where you have the signal probability is very large and the background probability is very small. So if you put a particular cut on this value, you basically define a particular signal region. So and this is what these classifiers all do. So the Langman-Pearson lemma, in other words, you can do a certain max. Okay, I should explain what this curve is. So this is a very important curve. It's called the ROC curve. It's the receiving operating characteristics. It's a plot that plots the minimum type 2 error as a function of the minimum by type 1 error. So this is type 2 error. It's basically the back 1 minus the background efficiency. And here you plot the signal efficiency. So a good classifier keeps signal efficiency high while the background efficiency low, or 1 minus background efficiency was high. So there's a theoretical limit set by this Neyman person, set by this. And then you can judge your classifier how good it is, depending on where it is. So a good classifier would be very close to that one. If you just randomly guess or did signal and background just blindly by maybe throwing a dice, then you should end up on this curve. So now you ask me how I pick where to cut. So if you cut, you set a certain signal and background efficiency. That means if this is, let's say my neural network follows this curve, I pick a signal efficiency of 70%, which gives me a background efficiency of 2%, and because my classifier is basically defined by this curve. So for 7% signal, I accept 2% of the background. So now, is this good or bad? It depends on what you want to do. If you want to measure the cross section, there you want, this can be proven mathematically, you want to maximize the signal over signal plus background. So what you have to know is how many signal events do I actually expect in my final sample. So this is an additional information that you have to put into in addition to what your classifier does. So if you say I expect 10 Higgs events and 2,000 background events, then you have these numbers and before the cut, and then you look at, okay, I then have to work with these signal and background efficiencies to get the maximum significance. This is called significance. If you want to discover a signal, you want to have the maximum over S over square root V. If you want to have a precision measurement, you might want to have a very high purity, so that you have less background events. You don't care about the high statistics, but you want to have a very pure sample. Then maybe you want to work very close to here, small signal efficiency, but almost no background. And trigger selection should be the other way around, should accept almost everything. And in TMBA, which is one of the packages, for instance, you can give in this number of signal and background events, and it will tell you actually the curve of significance or purity, and then you can actually pick your working point. But the working point, which is picked on this curve, depends on the expectation for signal and background. Okay, are you with me so far? I mean, these classifiers, all they do, they take all the information and combine it into one variable you then can use to define signal and background efficiency. How they do that?
The boxes will be giving you 6 of it. 9, 17, 24.
Okay.
In a sense, you can help them.
That's not
So this is important. Listen.
So let me come to machine learning. I'll only show you quickly the few classifiers that I wanted to introduce. Probability density estimators, and use the decision trees. So machine learning, that means you give the data set to the machine, and they tell you, okay, this neural net should look like this, or this PDE should look like this. And so they help you a lot, but you still need to do some tuning of the parameters of these classifiers. And in the end, you have to, and that's important, you should not rely on the Monte Carlo to tell you the efficiency that you expect from the data sample. So even if these classifiers tell you, okay, on Monte Carlo we have a signal efficiency of 75%, on real data that might not be true. It doesn't matter, maybe your classifier behaves slightly worse, doesn't give you the best performance, but the efficiency at the end you need to know very exactly if you want to quote your final result. So the efficiency itself you have to estimate from different sources. and so the systematic errors as well. Okay. So in principle, there are two very different methods. One is called the PDE method, and all these methods rely on that for a certain event, they can tell you, for a certain event that you measured, X, they can tell you how likely is it a signal, how likely is it what is the likelihood for a signal, or the PDF for signal, what is for background, and then you can make a judgment based on that. So they can do this in one dimension, in many dimensions, but they all have the same underlying principle. They look at your Monte Carlo data, and they look, okay, for a certain region I have that much signal Monte Carlo in this region and that much background Monte Carlo in this region. So what they all do, they build an n-dimensional PDF. The second part of classifiers, they don't build PDFs in space, but what they do, they put a separation between the signal and the background. So they know the signal is in this region, background is in this region. I should separate the two like this, and that way then they can classify events this way. And these are, for instance, neural network does like this, the boosted decision tree does like this, and support vector machines, if you hear the name somewhere, also separators rather than PDEs. Let me just skip. Projective likelihood estimation. This is the joint PDF. Again, in the bottom you have the sum of all PDFs. This is the joint PDF for the signal. This is the sum of the joint PDF for the signal and for the background. So this is basically normalization. This one, the joint PDF, in the projective likelihood approach, we assume all variables that I look at are independent. So I have an energy and momentum, and I treat them independent, which is not the case. But it's a very naive assumption. And if there's no correlations between the different input variables, that is actually a very good assumption. And then, instead of, and then this joint PDF becomes actually the product of all the single PDFs for the single variables. The advantages of using the projections of the joint PDF rather than the PDF itself is that even if you work in many dimensions, you still are reasonably protected from the curse of dimensionality. I'm going to skip that one. That tells you how to get PDFs from your data sample. They are using spline fits and
Roofit is a good bedtime reading.
Roofit? Yes.
Roofit, yes.
Yes. Well, so if you have a histogram and you want to turn this histogram into a PDF, what do you do? I think Joerg already explained that you can do a non-parametric fitting by putting a spline fit along the curve. So this you can easily automate. You put in TMA we have spline 2, 3, and 5, which means you take 5 points, you put a curve through it, and maybe turn the PDF into a PDF that way. What you can also do, if you actually know the parametric definition of that histogram, then you can use a package. This is called Roofit. For that you would have to know, okay, what is the function of that? What is the function that describes this histogram? If you know this, you can use Roofit. If you don't know it, then you have to use TMA, for instance, and you have to use the non-parametric fitting, which just takes the histogram and turns it into a smooth function, basically. Okay, and multi-dimensional PDEs that basically map out your joint PDF. They don't project, but they keep the joint PDF. For instance, if you look K nearest neighbors, I have an event measured in my data sample. I want to find out is it more Monte Carlo-like or more data-like. So what I do is I look in my Monte Carlo sample in the neighborhood of this test event, and if there's more Monte Carlo, then I say it's Monte. If there's more signal, then I say it's a signal event. If there's more background, I say it's a background event. So this is basically these multi-dimensional PDEs. They all work the same way. And if you want to know more about them, I'm happy to tell you because it's an interesting subject. Let me skip the curse of dimensionality. A boosted decision tree. That is, you might have heard about this. This was a very big success story in one of the, well, not so latest DESY results, where they did a single top measurement. They used boosted decision trees, and that gave them the best performance to actually get the last bit of information out of their data set. So this is the PDF. Okay, so it's not so animated. I would have liked. So decision tree is just, you take all the events that you have in a Monte Carlo sample, you find, okay, which of the variables separates a signal from background the best. And by best separation, you look at something that is called a Gini index, which gives you, it's sort of also called inequality index. So it tells you, if I split there, then I separate, have in both nodes the most inequality between signal and background, which is what you want to achieve, to separate signal and background. So you do this, and you take then a subnode, and again look at the Gini index and try to split that. In the end, you get a very long tree, actually much longer than this one. And then when you want to do event classification, you have to do a test event. You put it in at the bottom. You follow the decisions. So first, maybe you split at the first variable. If the event maybe falls in this category, you look at the other variable that was used here. Then maybe you go down here. In the end, you can decide whether it's more signal or more background-like. The advantage is that this method has very little tuning needed, which is a good thing because it almost always gives you a good result. However, decision tree this is a decision tree. It's only one part of the story. A boosted decision tree is not one decision tree, but a whole forest. So you take one tree, you put your whole data sample into it, and you find, okay, here's 90% of the time it classifies the event correctly, 10% it does a mistake. Then those 10 events, I give a higher importance. And then I use the same method again. I build a new decision tree where the errors of the previous round are made more important. So this new tree is actually more sensitive on the errors made in the previous tree. By doing this many times, and in the end, you sum up the result of all the 400 trees, of all the forests basically. You sum up. The final classifier is a linear combination of all the trees. Then this gives you a final number, which is actually a very well-performing classifier. It is stable. It doesn't need much tuning. And well, it has become very popular in high-energy physics. And for analysis, you might actually consider using a boosted decision tree as a first trial to get a good separation between signal and background. So in the summary, you see a plot of the zero using these the single top measurement, using decision trees, matrix element, Bayesian neural networks. Here's some literature, and now how do we proceed? What we have now is an output distribution for the signal and background, again on Monte Carlo. And you can either use these output distributions, you can use them to fit the data directly. If you have data that looks, let's say, has two bumps, then my bump might be background, and the left bump might be signal, the signal, and then when you fit for that, you already have the signal background matches. But what you want to do most likely is that you want to set a working point, throw away a lot of events, keep the ones, and hope you then have a more pure sample that you continue.
Maybe we could do something.
Yes.
Tomorrow there are 3 45-minute lectures about data analysis. Maybe you can continue some part of your lecture
Yes. So we can do that. I have only 5 slides left, and this is the last part. It's the estimation of variable properties. How, when you have then a final set after throwing away then most of the background, how do you estimate the signal parameters? And Gökhan, what time is that? Sorry. What time is that? Tomorrow morning?
Yes, 7:36.
Okay, so tomorrow morning we go then. We go through the estimation of variable properties for which we use the chi-square fit and the maximum likelihood fit, which are 2 of the estimator methods that are most commonly used. And that's then it. Please.
I have 2 questions. The first one is about the method, the native method that you said. That already requires that we already know that this an event is a signal or background, so
yes.
we can only apply this in Monte Carlo?
Yes. No.
So how can we apply this method in data?
Yes.
That's my question.
So in first approximation you can only apply it to Monte Carlo. You have to know if it's signal or background, because these methods, they are called supervised learning. And supervised learning means the classifier tries to say it's signal background, but you tell it in the end it's you're right or wrong. That's why it's called supervised learning. You can, if you're lucky and you look at some physics, there's a method of data analysis where actually from the data you know if it's signal or background. For instance, you know a set boson decays into 2 electrons, for instance. If you know one is an electron, because you measured it, then you know the other one is an electron. So, but this is not often the case. So yeah, you need Monte Carlo.
And the second is about the boosted method that you said.
Yeah.
So you said that we calculate an error with a larger weight.
Yeah.
We give it a larger weight in the error. So at the end, doing this many times, we come up with a result. I didn't understand this result. What does this result express? I mean, what is the meaning of this result?
Yeah. So in the end, there is. Well.
So how do we use it to?
Yes. Let me maybe to this picture and. So the result that you have these 400 trees, and you take your event that you want to test, put it in all the 400 trees. One tree says it's a signal, the other says it's a background. In the end, you sum all this information up, and the overall sum is a number, a real number, which might be here or here or here or here. So if it's here, you would say, okay, I don't take this event. If that number is here, you say, I do take an event because you decided to make your cut here. So to boost the decision tree, you put an event on top, it gives you back a real number, and then you see, keep it or not. Is that...
Also I have a question about supervised learning. So when you take the Monte Carlo sample to train the algorithms, we know that the Monte Carlo is not perfect. So how do you estimate this contribution to the error bounds of your final measurement?
Yeah, the fact that the Monte Carlo is... Yeah. So he asked, the Monte Carlo is never representing the data perfectly. And how do you take this into account? Well, first in the training, in the supervised learning, and then also later in your analysis. For the supervised learning, the answer is you don't. You say that Monte Carlo is a pretty good approximation of what we expect, what the real data looks like. You train on this Monte Carlo. If the data is a bit different, you might not have the best classifier. So you might, it might not be performing as well as you think. So maybe it's a bit worse. But in the end, that doesn't matter. Because in the end, what you do is the efficiency of the estimator throwing away stuff, you have to estimate on data anyway, or you have to find other ways to estimate this. So
how do you practice that estimate?
Yes, you. Well, in practice, maybe for some reason, for some things you have to use Monte Carlo, and you have to rely on that is correct, and you have to say, okay. But otherwise, like as I say, the double tagging method, where you know a set boson produces an electron positron, and you measure one, and then you know what the other one is, and then you can measure the efficiency on the other one of some of the selections you do.
Yeah.
That.
Can I add something?
Yes, please.
Also, what you can do is you can modify your Monte Carlo on purpose, shift some values in one direction or another, and see how your classifier behaves. Within normal assumptions and reasonable modifications, so after all, Monte Carlo is doing up to some extent, representation of the data with the error bars. You have some estimations of the error bars yourself, shift the values within these error bars, so you modify your event manually for each particle. For example, you shift the %, assuming there's some mistake, and rerun the classification to see if you get approximately the same result. If your classifier again classifies the events as you expect, it's okay. If it's completely off, then you don't trust this classifier, because if there is a problem with Monte Carlo, which cannot represent, which we don't see in the data, if the data is shifted, then you'll get completely wrong set of events selected. So the typical trick is you modify each input individually or combinations.
Well, I would tend to disagree, because what you do if you shift one parameter and then the classifier changes, that would mean that maybe the classifier is sensitive to that certain parameter that you have used to modify. If it doesn't change at all, maybe the classifier decided early on, well, this is a variable I don't care about because signal and background look the same for that particular variable. So you might be shifting it all around, the classifier will not change at all. So I think I would not worry so much that the classifier output changes. I would, because in the end it doesn't matter. In the end, it gives you a number, and you say this is sigma, this is background. If the Monte Carlo is wrong, it behaves slightly worse than what you expect. But the efficiency itself, you should measure from.
Yeah, if the Monte Carlo behaves incorrectly, we can discuss it offline.
Yes. Yes, if the Monte Carlo. Yeah. Yeah, let's discuss it offline.
So maybe there was a suggestion from the student, maybe at 9 o'clock we come back here to discuss the remaining of the slides if you want to discuss, either from this lecture or from the group lecture, and also we can look at the homework that you are going to do this evening. So instead of meeting at the minus 2 floor in the other building, let's meet here at 9 o'clock.
And yes, the other thing is about the previous lecture. The missing part was how to the homework was to extend this band class. But I think you can try to compile and make this band library at home, and we can discuss it tomorrow morning. But maybe this is more of interest to you. Yeah. You tell tomorrow morning what you should do.